All right, shifting gears back to our warm-up and limits, right? So we have some variations on these below, okay? And I'm curious how you might naively approach these, okay? So I'll give you a moment to look at them and think, and then resume the video. Okay, when I say naively, I mean like we're just gonna take a shot and see what happens, right? So if we're approaching a limit at a certain point, we're gonna try putting it in, right? So this one we're gonna be okay, and it'll work, and then we'll build some confidence. So we just get 0. Um, this one we get, let's see, be 0 over 0, right? I think, I think. Yeah. So then we cry a little bit, but we're like, 0 over 0, that's just infinity, right? Um, and so we're like, oh, okay, we're moving on. And then this next one, we get 0 over 0 again, and we're like, infinity? And then we're like, okay, well, that's good. And then when we go to infinity, we're like, oh, it's just the ratio of the leading coefficient, so this is just 1. Okay, that's a horizontal asymptote. All right. And so, yes, um, some of these will work, but more generally, the ones where we get 0 over 0 are problematic. Okay. Um, and when we see something where we get 0 over 0 or infinity over infinity, those are called indeterminate forms. Okay. Infinity over infinity, negative infinity over negative infinity, plus or minus infinity over plus or minus infinity, those are all indeterminate forms. 0 over 0 is indeterminate, and they're called indeterminate because we can't find the precise value, right? Some things that are not indeterminate, 0 over infinity, right? 0 divided by anything is always 0. 0 to infinite powers, right? 0 multiplied together however many times is going to be 0, right? Infinity plus infinity, well, you add two very large things together, you get something that also is also very, very large. So those are not indeterminate. So to handle these things, we have a rule. It's called L'Hopital's rule. It looks intense, but it's actually quite nice in practice. Okay, so we have to have two differentiable functions. Okay. Um, and then we also have to have the g prime is not 0 near our limiting value a, okay? And we also have to have that either, f and g have limits of 0, or they both have limits of infinity, okay? You can't necessarily mix them. That's what the indeterminate form is about, because it says, when you take their quotient, you get an indeterminate form for that limit, okay? And so then with that indeterminate form known, we can then say, by L'Hopital's rule, that the limit of our original quotient is the same as the limit of the ratio of their derivatives. Okay? And so then we just differentiate numerator, differentiate denominator, and then see what that comes to for a limit. If it's another indeterminate form, we go again, and we keep on going until we get our answer. Okay. And the only thing that I'll say with this rule, and I'm going to hammer this in because it is very commonly forgotten, before you use L'Hopital's rule, you need to verify that you have an indeterminate form. Okay, you can't use this willy-nilly, right? If we look at the theorem, it says suppose, so these are hypotheses. You have to check that these things are differentiable. So can you find the derivative? Is the derivative of the denominator function 0 at any place near our limiting value? And then, do you have indeterminate form? Okay, so you have to check these things before you use the rule. Okay, and then also know that this is valid for one-sided limits and limits at infinity too. Okay, now normally I would prove this, but and the reason we talked about the extended mean value theorem is that the extended mean value theorem is used in the proof. Okay, I'm not going to do that. Instead, I have posted a link to the proof using the extended mean value theorem. There are other versions of the proof too. So if you are eager to see other types of proofs, you sure can. But that I think is all I am going to. We can do a couple as warm up. a couple examples for this video, and then we're going to move on. So first one we actually saw. Okay, so if I look at this, right, we know the answer is 1, right, by horizontal asymptotes, but we could also recognize that, okay, this is, so as I think about this, this is infinity over infinity, right? Because numerator would go to infinity, denominator would go to infinity, so I'm saying that this is an indeterminate form, so then I can say, okay, by L'Hopital's rule, this is going to be equal to limit as x goes to infinity of, now differentiate the numerator, differentiate the denominator, okay? And then I'm thinking, okay, again, naively, right, looking at the numerator and denominator separately, okay, I could divide everything by 2. Big deal. But then numerator would go to infinity over infinity, so then I'm going to use L'Hopital's rule again, and I get limit as x goes to infinity, of 2 over 2, which is also known as 1. Okay? So, there I have the limit a different way, not necessarily using L'Hopital's, or not necessarily using horizontal asymptotes or that multiplication strategy that we've seen before. Okay? All right. All right, and one more example here, and then we're going to cut to a different video. So limit as x approaches 1 of this, so then if I naively do that substitution thing, right? If I put in 1, I get 0 in the numerator, 0 in the denominator. Okay, then let's use L'Hopital's rule. Okay, so then let's see, this would be limit as x approaches 1, and I should do L'Hopital's rule there. Limit as x approaches 1 of ax to the a minus 1 over bx to the b minus 1. Okay? And now, actually, I think this is okay to substitute in, right? If I substitute 1 in, I get a in the numerator and b in the denominator, and I'm done. Oh, okay. 1 to any powers 1 for both numerator and denominator. Okay, so there we go. We have a few quick little examples of L'Hopital's rule. We'll see the others in the next longer video.